Earlier you learned about gravitational potential energy, and before that you learned about kinetic energy. So now we're going to introduce the term mechanical energy and talk about something very, very important about mechanical energy, and that is it is conserved. We call it a conserved quantity. So first of all, what is mechanical energy? The definition's fairly simple or straightforward. Mechanical energy is the sum of an object or a system's kinetic energy and potential energy. Okay, so you just take the object's kinetic energy, you add it to its potential energy, and whatever the total is, we call it the mechanical energy. It can be for an object by itself, but sometimes we talk about a system of objects if you have multiple objects interacting with each other. You can think about two objects tied with a string, and there's a pulley, and they kind of move together. There were a couple of optional examples related to that in previous weeks. Okay, so that's what mechanical energy means. You just add kinetic and potential. Technically, it's all of the different kinds of potential energy, but in grade 11, you only really worry about gravitational potential energy. So the main thing that's very important about mechanical energy is that it's conserved. Actually, before I talk about that, I need to distinguish between conservative forces and non-conservative forces. So all forces can be split into one of these two categories, and there is a way to define what a conservative force is. That would be really confusing if I tried to do it this year and also try to do it online. That would be pretty hard. So I'm just basically going to tell you which forces are considered conservative and which ones are considered non-conservative. So all conservative forces, we have a potential energy that we define for it. So there's gravitational potential energy has been defined for the force of gravity because gravity is considered a conservative force. And there's three others: electric, magnetic, and elastic. So all four of these forces, there's a formula for each one of them for its potential energy. But that's not true for the non-conservative forces. Okay, they do not fit the definition of conservative force, so they don't have any potential energy formula for them. Examples would be normal force, friction, applied force, and tension. Okay, so this is going to be a pretty confusing slide because I didn't actually give you the definition of a conservative force. You kind of have to just memorize it, that it's these four. Or really, you only have to memorize that gravity counts as a conservative force because we use that one in grade 11. Okay, so now I'm ready to talk about this important principle called the conservation of mechanical energy. So the statement reads, if the only forces that do work on an object or system are conservative, then the total mechanical energy of the object or system remains constant. Okay, so if the only forces that do work on an object or system of objects is conservative, then the total mechanical energy of the system remains constant. That means the object could be moving or the system of objects could be moving. But if you calculate the mechanical energy at one point in time and you get a number, and then the object moves a little bit, and then you recalculate the mechanical energy after it's moved or done some stuff, the answer you get should be the same as when you calculated the first time. Okay, even though it might have sped up, slowed down, changed its position, if you calculate kinetic plus potential, that total number should stay the same, as long as the only forces doing work on it are conservative. So that means we pretty much have to be in like an ideal situation. It's got to be frictionless so that friction's not doing any work on it. There can be no air resistance. no applied forces. It can basically only be gravity in grade 11. And then this principle will hold true. So as one example, let's just consider a rock released from rest. A rock is released from rest and then it falls down. So here's a bar graph showing the energy of the rock starting at the top. Okay, so when I just let go of the rock and right before it starts falling down, well, the kinetic energy would be 0 at that point because I released it from rest. It's not moving. So the kinetic energy is at 0 joules. The gravitational potential energy, U, well, you'd have to calculate it with mgh after specifying a reference height. And I just made up a number there. Let's just suppose that it had 40 joules of gravitational potential energy. And that means that the mechanical energy, which is K plus U, would be 0 plus 40, which is 40 joules. Okay, now we're going to let that rock fall for a little bit of time. Okay, just a little bit of time. So what happens when a rock falls? It gets lower. It gets lower, but it also speeds up. So it loses one kind of energy. It loses some gravitational potential energy. And it gains another kind. It gains kinetic energy. And with a bar graph, you might see something like this. So perhaps the rock fell down a bit. So the U bar, the gravitational potential energy bar, dropped from 40 to 30. Well, where did those 10 joules go? They don't just disappear and go nowhere. Those 10 joules had to be transformed into some different kind of energy. And in this case, since the rock sped up, that means the kinetic energy increased. And it must have increased by the same amount that the gravitational potential energy decreased by, which is 10 joules. So then the mechanical energy, however, stays the same at 40. 10 plus 30 is still 40. Okay, so this principle, this conservation of mechanical energy, is saying that the total, the ME, has got to stay the same as long as it's only conservative forces. And for a rock falling down, gravity is the only force, and gravity counts as a conservative force. We are ignoring air resistance. Then we can consider the rock when it's really close to the floor, really close to the ground. Well, then it's lost even more of its height, so it's lost even more of its gravitational potential energy. And it picked up even more speed, so its kinetic energy went up even more. So the bar graph would look like this. The gravitational energy, since it's down near the ground now, the height's basically 0. So the gravitational potential energy is basically 0. And that means all 40 joules are now in the kinetic energy bar. And the total mechanical energy stays the same at 40 joules. The second example here shows a projectile. Okay, so think back to a projectile. Anything that gets tossed, it travels through the air, and it's only gravity affecting this ball. So it makes this parabolic path, if you may remember from Unit 1. So at the beginning, I made up a couple of numbers. Let's just say the ball was launched, and it was launched with 100 joules of kinetic energy. That's the energy due to its motion, its speed. And if we set the reference level to be where it was launched from, then the gravitational potential energy would just be 0 joules. Okay, it's starting at the bottom. When you add 100 plus 0, you get 100. So the mechanical energy is 100. So then the ball rises. Okay, the ball rises a bit. So what happens to the energies? Well, if it gets higher, that means it gets more gravitational energy. But it can't just magically get more energy. It must mean that some other kind of energy went down. And in this case, it would be the kinetic energy went down. So I filled out the values for all of them, actually. But on its way up, it's slowing down, right? The ball is slowing down as it gets higher and higher. So you see the kinetic energy value get smaller and smaller, 100 to 50, down to 20. And at the very top, I have the kinetic energy at 10 joules. It's not 0, It's not zero because it's not totally at rest. It's still moving forward a little bit, so it should not be at 0 joules. So the kinetic energy is going down as it slows down. That means a different kind of energy is going up. That would be potential. So the potential energy went from 0, and then here's 50 to 80, and up to 90 here. But all throughout this whole projectile launch, the total mechanical energy stays the same, 100 joules. And when you add up K plus U, it always equals the same number. That's the law of conservation of energy. And the same thing happens as the ball goes down on the other side. We talked about that in the previous example. As the ball falls down, the kinetic will get faster, get higher, and the gravitational will get smaller. But the total is always the same number, in this case 100 joules. Okay, so that's the law of conservation of energy. I'll just show one more thing. I'll show a little cool simulation here. So there's a bar graph here showing the energy of the skateboarder. Right now everything's at 0 because he's not moving or she's not moving, so the kinetic energy is 0. They're on the ground, so it's not like they're high up, so the gravitational potential energy is 0. This thermal energy, which I'm going to ignore for now, and then the last bar will just be the total when you add it all up. So if I raise the skateboarder, if I hold her here at rest, look at the bar graph. The kinetic is 0 because I'm holding her at rest. She's not moving. The potential is big now. Okay, I lifted her up, so she gained a gravitational potential energy. And the total energy bar is the same level as the gravitational potential because that's the only kind of energy there is right now. And I'll let go. When I let go, just watch what happens to the bars. So this is basically, I think, beautifully showing an energy transformation. Energy is simply switching from kinetic to gravitational potential, vice versa, as the skateboarder goes up and down, up and down. But all the while, the total amount of energy never changes. That's the law of conservation of energy. The total energy never changes. Now you may wonder, well, gravity's not the only force here. You said this only happens if conservative forces are the only forces that do work. But there's like a normal force, right? And there's friction. Well, actually, there's no friction. Okay, I set up this to be a frictionless situation, so kind of cheating a bit. So there is no friction. Well, what about the normal force? Normal force is not considered a conservative force. However, the normal force, I'll put it in slow motion. The normal force is not doing any work at all on the skateboarder. Remember, work done by a force can be positive, negative, or 0. If the force is perpendicular to the motion, then it actually does 0 work on the object. And in this case, the normal force is always perpendicular to the surface, and the skateboarder is always moving parallel to the surface. So the normal force and the direction of motion are always 90 degrees to each other. Right? Always they're 90 degrees to each other. So the normal force is never actually doing any work on the skateboarder. So it does not violate the conditions for conservation of energy. I'm just going to do one other thing here. So I'm going to drop the skateboarder from a height. So she'll fall on the track. Boom, falls on the track. And you may have noticed I got a little bit of thermal energy. Okay, so, oh, and oops, she went too fast and fell off. But why did that little bit of thermal energy showed up when she landed on the track? Because that's like a collision. Boom, she lands on the track. That causes some particles, some molecules to jiggle a bit more. And the more particles jiggle, the more thermal energy they have. That's why it showed up there. All right, So that's it for this lesson.